Good morning. Welcome back to PL. Today we'll move on with the lambda calculus. And then first, let me remind you that assignment 5 is due this week on Friday. So make sure that you follow the formatting requirement for that assignment because I don't want to see any handwritten lambda expressions in there. It's already hard enough to grade when everything is typed up. So make sure you do that to follow the directions. If you have any questions on beta reductions that we talked about on Friday, let me know right away because from now on we're going to beta reduce like there's no tomorrow. So hopefully you're getting comfortable with that operation. So now we're going to step back a little bit and do some more interesting things with the lambda calculus now that we discussed the basic operation, which is that beta reduction and alpha conversion. Last time we defined this to be a beta redex, that is an application where the first component is a lambda abstraction. These are the only kinds of expressions that we can reduce using a beta reduction, which is just a substitution. Now remember, to reduce or evaluate this kind of expression, you have to strip away the lambda p. You got to return the value of the body b after you have substituted a for p in it. That's what a beta reduction is. Now, so this is a beta redex, and we're going to underline those beta redexes before we reduce them in the assignment, say. But there's something missing here, which is that because the b and the a can be any lambda expression as complex as you want them to be, there could be a beta redex inside of the b, and there could also be a beta redex, or many of them, inside of a. So the question is, when there are several beta redexes in an expression, which one do you reduce next? There's a choice of which beta redex to reduce. And choosing which beta redex to reduce is called a beta reduction strategy. So that's what we mean by a reduction strategy is which beta redex do you reduce next? Or do you choose to reduce next? So do you choose to reduce the first one from left to right, or the one that's at the top level? I notice this blue one is what we call the top level redex. This is also called the outermost redex because it's outside. It's not contained in any other redex. Whereas any redexes in B or A are contained inside of that blue one. So which one do we pick is the question. One inside, a nested one, or the topmost or the outermost? Excuse me. Everybody understand the reason why we need to discuss these strategies. A strategy is in what order do you pick which redex to reduce? And does it even matter the order in which you do it? Are there any consequences for picking one strategy over the other? And in this class, we're going to pick two different strategies. As a spoiler, the strategy will be you always pick the outermost first, so the blue one, or you always pick, an innermost first, one of those red ones. Those are the two strategies. So does it matter which strategy you use? In particular, if you pick different strategies, could you get different results? That would be a problem, right? Because if your program gives different results depending in which order you evaluate it, you better be careful which strategy you use. So we're going to answer all of these questions today. We're going to explain a couple of different strategies, and we're going to explain and give an answer to these questions. So before we dive into that, though, are there any questions about this introduction, this motivation for why we're discussing reduction strategies?
As far as like alpha conversion, like precedence?
First of all, so I didn't talk about alpha conversion. So alpha conversion is not an important operation. It's only used as a sub, in one of the cases of substitution. So remember, alpha conversion does not does not make progress towards getting the value of the program. So this has nothing to do with alpha conversion, other than alpha conversion is used down at the bottom in one of the cases. This is just about beta reduction. And second, you talked about precedence. Yes and no. Just ask the question again later on. It's not really just precedence. By precedence, you mean precedence of operators, whether you evaluate this before that. So it's related in the sense that, yes, we're going to evaluate something before something else. But you'll see it's more important than precedence. It's not quite limited to that. So let me just stop at that and then ask me again after we discuss the next couple of slides. Any other questions? So just remember, everyone, not to confuse beta reduction and alpha conversion. Here we're only talking about beta reductions, right? Which order we do those. We don't have a choice for the alpha conversions, because once you pick a beta reduction, the algorithm tells you whether you have to do a conversion or not. So the first question is, if you pick two different reduction strategies, could you get different results? And the answer to this question is what we call the Church-Rosser theorem. So Alonzo Church invented the lambda calculus. Rosser was one of his students. And they proved this theorem is that if two different strategies are used to reduce an expression and they both lead to some answer, then they will always give you the same answer. So I'll just say it again. If you have a choice, you have two different reduction strategies, and when you apply each one of them, they give you some answer, then this theorem guarantees that they will always give you the same answer. So do different strategies lead to different results? Here we could say no, but it's a qualified no. So the answer is really yes and no. Why? Because of this condition. If two different strategies lead to an answer, so if by using a strategy you get some answer, and by using another strategy you get another answer, the theorem says they will always actually be the same answer. However, the theorem doesn't say that when you use a strategy, you're guaranteed to get an answer. And we'll see an example on the next slide. So there's an if here, right? If a strategy gives you an answer, then it will always give you the same answer than any other strategy that gives you an answer. But the theorem doesn't say that every strategy will terminate and give you an answer. So you see why this is yes and no, right? There could be a strategy that gives you an answer, and there could be a strategy that doesn't terminate. So in that sense, they don't give the same result, right? Because one of them gives you some answer and the other one doesn't. What the theorem says is that if they both give you an answer, they will be the same one. That's a little bit different. So the theorem doesn't say that every choice you make will be a good choice. It doesn't mean that every time you pick a strategy, it will always terminate. And even worse is that if a strategy doesn't terminate, so it doesn't give you an answer, it doesn't tell you anything about whether there is an answer or not. You may have to try some different strategy. So in other words, it could be that there is an answer, one strategy gives it to you and another one doesn't. The theorem doesn't guarantee that you will always get an answer, and therefore it doesn't guarantee that you always get the same answer. So I just want to stop here. I'm going to give you examples in a minute. The theorem says exactly what it says. If two strategies give you some answer, they will always be the same. But it's quite possible that one strategy will give you no answer and the other one will. So does it matter which strategy you use? Definitely, as we're going to show in a minute. Do they always give you the same answer? Yes and no. If they give you an answer, it will be the same one, but sometimes they won't give you any answer at all. Does that make sense? It's kind of an important result in the theory of the lambda calculus and in the theory of computation in general. So in case you're a bit confused about this general thing, let's just do some concrete example. So here is a lambda expression. Let me zoom in a little bit. So this is a completely fine lambda expression. We saw a very similar one last time, but it's a little different, this one. So how many beta redexes are there in this lambda expression? There's only one here. Right? This is a beta redex, meaning the whole thing is a beta redex. Everybody okay? So I'm going to underline it. So now I'm going to go ahead and reduce it by doing a beta reduction. Who can tell me what the answer is when you beta reduce this beta redex? You get exactly the same thing. Why? Because remember, this is a beta redex. X is the parameter. This thing is the body. So what do you get when you return the value of this body xx after you substitute lambda x dot xx for x in it? While you strip away the lambda x dot, you replace this x by this x by this, and you'll get exactly the same thing, which means you get the same expression, which means it's not reduced at all. It's identical, which means you could just better reduce it again, and you get an infinite loop. It never finishes. You can reduce it over and over again. You always get the same expression. You're not making progress towards the final answer of this program. So in fact, there is no value or there is no result because it goes into an infinite loop. Does that make sense? This is what we mean by the theorem doesn't say that it's ever going to terminate. Sometimes it will, sometimes it won't. It just says if it terminates, a strategy will give you the same answer as another strategy that also terminates. Now, this is called non-termination because it's an infinite loop. Is this good to have an infinite loop? Well, in general, in programming, it's not a good thing, right? An infinite loop means no answer. In some cases, it's useful, but most of the time, it's not. But in some sense, it is a good thing that you can have an infinite loop in the lambda calculus. I'm going to argue now in a sentence that it's not a bad thing that to have an infinite loop. Why? Because many students believe that the lambda calculus is so simple, right? The grammar is so small that it's a toy language. But we're going to say, I'm not going to prove it, but we're going to convince you that the lambda calculus is as powerful as any programming language you use every day, Java, JavaScript, Python, whatever. And it better have infinite loops because you can have infinite loops in all of these languages. So if it's as powerful, it better have infinite loops as well. And here it is. We do have infinite loops in the lambda calculus. So in that sense, it shows the power and the limitation of the lambda calculus, the same way that the other programming languages you use every day also have a lot of power and a lot of limitations. They can have infinite loops, right? Okay, so when I say counterexample, I mean a counterexample to the theorem. The theorem does not say that, so it's not a counterexample. It's just to be clear that the theorem never says that any strategy is guaranteed to terminate. It just says if the strategy terminates, blah, 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 right? Now, here is maybe an even worse example, or counterexample. So look at this lambda expression. Now, when you look at this one, you will realize that there is more than one beta redex in this one, right? So there is a beta redex. There's the same beta redex inside right here. Be careful, the arrow has to start under the opening paren and close under the closing paren. So the last paren is not in the beta redex. So everybody understands this beta redex is the same as this one. And here is another beta redex. This is also a beta redex, this whole expression. First of all, by now you should be comfortable identifying beta redexes. Everybody agrees? Has anybody have any question about how I identified those two beta redexes? Okay, we have two function calls in this thing. So this is a function and this is its argument. That's the big one. And then this is a function, and this is its argument. So we have two beta redexes. So now we have a choice. Like here, we didn't have a choice, by the way. There was only one beta redex. So there was no choice of strategy. But here, there is a choice. So remember, there's two strategies we're going to describe starting on the next slide. One is we're going to take the outermost beta redex first. And the other one is we take the innermost. So everybody understand, again, this is the outer redex because it's not contained in any other beta redex. It's on the outside, right? It's the top level. That's called the outermost. And this one, so I'll write it down. Well, I won't write it down, but the big one is the outermost. You can take notes. You should take notes. And this is called the innermost. Why? Because it does not contain any beta redex inside of itself. So it's at the inner part, it's the innermost. Anyway, remember those names. We're going to use them a lot starting from now. But do you agree that I could pick either one to get started with? So let's say I always take the innermost first. So I'm going to start reducing this one. So let's do the innermost first, always. So I'm reducing this. I'm going to get a new expression, including the whole thing with this beta reduced. But then I'm still going to have this one in there, so I keep reducing it. So everybody agrees that if I pick this strategy, I'm going to get an infinite loop again to reduce this expression. Because if I always pick this one always evaluates to itself, so this will never end. So far, so good. So if I pick the innermost strategy, innermost first, I'm going to get in trouble here for this entire expression. So let's try the other strategy. The other strategy is you always pick the outermost first, the outermost redex. So what happens when you reduce this expression by considering the big one? What do we get? Anyone?
Just returns M.
Exactly. So in one step, right, if you do a beta reduction here, you get M. Why? Because what do you get when you return the value of M, the body of this thing? So you strip away the lambda x, you return the value of M after you substitute this entire thing for x in M. Well, there's no x in M, so this is M. In fact, this is a constant function, right? It's a function that ignores its argument and always returns M. So it doesn't matter what you apply it to, right? In one step, it will return M. And you see now you have two strategies, right? Strategy number one, which returns M for the same expression, whereas strategy number two returns an infinite loop. It means returns nothing. There's no value return, right? This is an infinite loop. So this is a counterexample to the theorem, while quote unquote, because the theorem never, so it looks like we're getting two different results based on the strategy you choose. So it looks like, we get two different results. But remember, the theorem didn't say that you would get the same result all the time. It said, if both strategies return a value, then it's guaranteed to be the same. But in this case, this theorem doesn't apply because this one doesn't give a value. So it doesn't say anything. The theorem doesn't apply to this thing. Okay, so this is the first segment I wanted to do today on the Church-Russell theorem. What you need to realize is there are different strategies that we could use. We're going to discuss those two, the innermost first and the outermost first. And what the theorem says is that be careful which strategy you choose because some of them may give you an infinite loop, some of them may not. But if they both give you an answer, then at least you're guaranteed that it will always be the same answer. So it's not possible that you would pick a strategy and you would get one answer one way and then a completely different answer or even a slightly different answer the other way. But what's possible is that one of them or both of them may not give you an answer. Notice here, by the way, both strategies will give you an infinite loop, right? Because since there's only one beta redex, it's both an innermost and an outermost. So there's only one way you can do this one. And in the two strategies end up with the same behavior, which is an infinite loop. So again, the theorem just says if the strategies terminate, then they'll give you the same answer. That's all it says. But it is still a useful theorem. It tells you there will never be two different answers for the same program, which is good. Okay, so what I want to do in the next segment is I want to dive into these different strategies a little bit more, the innermost first and the outermost first. And we're going to give them their official name. This is called the normal order strategy, and this is called the applicative order. But in fact, they have many names. So, but in the lambda calculus, we're going to call them the outermost first and the innermost first.